part. Now how to calculate the stress in that spring. Okay, a stress in helical spring of circular wire, cross section of that wire we are going to consider as a circular cross section, that we will try to calculate. Okay, then which type of stresses will be induced in that wire, that first of all will calculate or will find, and later on its mathematical derivation will find out. Okay, for that you can see the cross section of the spring is shown in this diagram. Okay, here also the cross section of the spring is shown in this diagram, whereas in both cases we are going to consider that helical compressive type of spring. Now in this helical compressive type of spring, we are going to consider that small d is the diameter of wire from which the spring is manufactured. Okay, and capital D is the diameter, coil diameter of that spring. Okay, or mean diameter of that spring. Got it? So N we are going to consider as a number of active coils. G, number of active coils, if the total number of coils are given in the spring, can be calculated as a number of active coils from previous table which we have seen in the previous slide. Then G is we are going to consider as a modulus of rigidity of the spring material. W as the axial load which is applied on the spring, compressive load which is applied. Tau is the maximum shear stress induced in the wire, that in this wire, spring wire. C we are going to consider as the spring index, that is nothing but the coil diameter divided by wire diameter. P as a pitch of that coil of the spring, and delta as a deflection of the spring as a result of axial load W. Okay, these are terms which we are going to consider while we are calculating the stresses which are induced in this spring. Now we'll consider first of all that diagram in which we have seen in the compression. Okay, the load which is acting, that is W, is tending to rotate that wire. What is going to happen in the spring? This W is trying to rotate that wire, right? It is going to get compressed, means that rotation will be take place. And as you know that in case of any rod, if the rotational action is taking place, which type of stresses will get induced? कुठल्याही स्प्रिंगला ज्यावेळेला आपण फ्री ठेवतो त्यावेळेला त्याच्यामध्ये स्ट्रेस नसणार आहेत कुठलेच, पण त्याला ज्यावेळेला लोड करायचा प्रयत्न करतो त्याचा अर्थ काय होतो की त्या दोन कॉइल मधलं अंतर कमी होतं. दोन कॉइल मधलं अंतर कमी होतं याचा अर्थ काय आहे की आपण त्या जी वायर आहे त्या वायरला असं रोटेट करून, म्हणजे टॉर्शनल टाइप ऑफ स्ट्रेस देऊन त्याला आपण कॉम्प्रेस करतोय. जर त्याच्यामध्ये टॉर्शन किंवा त्याच्यामध्ये रोटेशन झालंच नाही तर दॅट स्प्रिंग विल नॉट गेट कॉम्प्रेस. Okay, for example, if we take the railway wagon spring and if we stand on that, whether it will get compressed? No, it will not get compressed. Whereas even you can take spring of two-wheeler suspension and if by hand if you want to press it, it will not get compressed because the load which you are going to apply on that is not sufficient to create the deflection in that spring. Now when spring is getting deflects means what? What is going to happen? If you imagine any spring and if you are going to compress it, it means that each and every turn of that spring is rotating. That wire is going to get rotated. Otherwise, we'll take an example of this. I will elaborate this diagram. Okay. If I apply load here, what is going to happen? These two coils are coming together. They are coming together means what? The distance between that two is going to get reduced. And how it is possible? It is possible only when if you apply load and if it is going to get rotate. Okay, because you have created rotation here and that distance you have maintained between these two coils. If it gets unwound, you have wounded. म्हणजे आपण त्याला असं रोटेशन पीळ देऊन आपण त्याला दुसरी कॉइल तयार केली. तो पिळ जर निघला, that means it will get compressed. That means distance will get reduced. Getting me? So while we are applying load, it is going to create rotary action in the coil. Okay, if you have understood it, then we'll go further. Otherwise, let me know whether you have understood it or not. हे तुम्हाला समजलंय का नाही? Hello? Salim Sheikh. Ah, yes, yes, sir.
Yes, sir.
Have you got it?
Yes, yes.
Okay. For example, if you are going to create any spring ज्यावेळेला आपण तयार करतो, Sushant Jadhav is saying type of stress. Okay, we'll go later on to the stress. Stress, while you are going to rotate any shaft, or when you are going to create the rotation any rod, which type of stresses will get induced? Torsional stresses. And torsional stresses are basically shear stresses. Okay, shear stress will get that. We can say combined torsion. We can use maximum shear stress theory, or we can use maximum principal stress theory for that. That we have seen while we have designed the shaft. Shafts are designed based on two theories: maximum principal stress theory and maximum shear stress theory. Now basically, shafts are, when you are going to rotate any shaft, it is undergoing for the shear. Okay, so torsional stress is going to create basically shear stress, and that can be calculated by means of Morse circle. Later on we will see. But have you understood by that procedure by means of which the spring get compressed? Hello?
Yes, sir.
Means that spring gets compressed by creating rotation in that coil, right? So rotation is created, and then afterwards that spring gets compressed. So while we are going to create that rotation, torsional stresses will be induced. So our basic question is that how to calculate that twisting. That twisting is nothing but that torque, or it is also called as twisting movement. If we are going to apply W as a load on the spring, then how we can calculate that twisting movement of that spring? Okay, that is first question. And then afterwards we can calculate the stresses which are induced in that. The torsional stresses will get induced. Okay, and in that torsional stresses, if we take the second diagram, I will again take this diagram to next slide, where we are going to explain it here. Okay. In this diagram, if we elaborate it, this load W is going to create this torque. Okay, and we are going to calculate this torque. Okay, so this torsional stresses, that is nothing but load divided by cross-sectional area of that wire. Okay, so this load which is applied divided by the cross-sectional area is pi by 4 d square, that is small d square, and hence we are going to get this shear stress, that is called as direct shear stress due to load, because when load is applied, it is directly will get shear. Okay, and here we are going to calculate direct shear stress, and that is load divided by cross-sectional area. Okay, that is 4W divided by pi d square. So where d is small d, and this small d is nothing but the wire diameter. Okay, so we have calculated this tau 2 shear stress, direct shear stress. How it is going to happen here? This torsional shear stress and direct shear stress, they will get combined together. Okay. No doubt that who has asked that question? Sushant Yadav has asked question that stress, which type of stresses will get developed. Now here, these two type of stresses will get developed. One is that this W is directly want to shear this wire, okay, and that can be calculated, that stress can be calculated as a tau 2, that is load divided by cross sectional area. Okay, later on we'll decide that number of coils and number of turns, that we'll see later on. But basically here this wire will get shear because of the externally applied load W. Okay, and second one is these torsional stresses. Now these torsional stresses are compressive to one side and tensile to the other side. Okay, so this is what the torsional stresses are. So we have to now calculate torsional stresses. And if you are going to combine this together, then resultant torsional stresses, that is, if we are going to consider the maximum shear stress theory, okay, and resultant torsional stresses, that is direct if you are going to consider the principal stress theory. Okay. So how to calculate it? Take your own time for calculating or for understanding the stresses. Now this total shear stress which will be induced in that wire, that will be the direct shear stress plus or minus, okay, to the torsional shear stress. Now this torsional shear stress will be added or subtracted from the direct shear stress. So this torsional shear stress which we are going to calculate is 8WD divided by pi dq. Okay, how we calculated it? By means of W divided by, okay, and that simple equation which we have written as Gj by where is the interested insert equation. So which basic equation we have used for deriving this equation? T by J is equal to what? Tau by R. R is nothing but D by 2. Okay. From this, we have calculated this T1 value. Now here we will write this as a T1. Here we have to apply the torque. Torque is nothing but, again here we can put force multiplied by radius. This force will be the W multiplied by radius will be D by capital D by 2. Okay, J of that wire, that will be pi by 32 D raised to 4. Tau D by 2 here. We have to write here as D by 2. Okay. So from this equation, we are going to get value as 8WD capital D divided by pi dq. And in that, we are going to add or subtract direct shear stress that we have calculated as a 4W divided by pi d square. Now further, if you are going to solve this equation, okay, so maximum shear stress we will consider, and maximum shear stress, that is nothing but when we are adding these two. If we are going to subtract this tau 2 from tau 1, it will become minimum. we are going to design this spring for maximum shear stress. So maximum shear stress is 8wd capital D divided by pi small d cube plus 4w divided by pi d square, right? Small d square. So we can take this 8w pi and d cube common. So remaining value will be 1 plus, just a minute. Okay. Now this maximum shear stress, that is total torsional stress plus direct shear stress, and this 8w capital D divided by pi d cube we are going to take common. Here when we are going to take this 8 as a common, this 4 multiplied by 2, that means 2 we have to divide here, and as we are going to take this d3 common, that's why 1d has to be multiplied and divide for this 4w divided by pi d square. Okay, so this equation will become as a 1 plus small d divided by twice of capital D. Now if we put value of this capital D divided by small d is equal to C, okay, we have to take vice versa of that. It will become 1 over C, okay, 1 by C. So we are going to put this value small d divided by capital D as a 1 by C. So this equation will become 8wd divided by pi small d cube into bracket 1 plus 1 divided by twice of C. Okay. Now here 1 plus 1 by twice C, if you are going to put as a Ks, that is shear stress factor. Don't bother about this factor because every time it is not necessary to take this Ks. Okay, we can directly put value of W, capital D, pi, and small d cube, whereas C also can be calculated from the capital D and small d. Just for simplicity, this Ks has been introduced here. Otherwise, this Ks is not necessary. So it will become Ks multiplied by 8W capital D divided by pi small d cube. From this, we can calculate the maximum shear which will be induced in that wire. Okay. Now just here, one note has been mentioned that this shear stress factor is nothing but the shear stress factor due to shear multiplied by shear stress factor due to curvature. Okay, this is considered at very micro level. If you are going to calculate the exact shear stress which will get induced in that coil, and if you are going to consider that effect of curvature also. Now, as we know that we are going to simplify each and every equation by considering or by neglecting some things. Sometimes we can neglect this effect of curvature also, and we can take this K as a Ks only. Okay. Any question related to this? Hello? Do you have any question? If not, we'll go further. Now we are going to calculate deflection of helical spring of circular wire. Okay, that is how much it will get deflect. Deflect means how much twist will occur in that in terms of deflection. That is, we can measure it in theta, because we have seen while we have designed shafts are based on principal shear stress theory, then principal normal stress theory, and on rigidity base, right? If you are remembering, then based on rigidity, shafts are designed. Likewise, here also, this wire is designed based on rigidity, torsional rigidity. Here we are going to calculate the strength of that wire based on torsional rigidity. Okay. Now let us consider L as the active length of that wire. Active length means total length of that wire. Okay. When it is unwounded, what will be the length of that wire? When the spring is unwounded. Okay. That means it will not remain as a spring. The coil which has been formed, it will not remain as a coil. It will become a straight wire. Okay. So that length, if you want to calculate, that is considered as a L. So that is calculated as a length of one coil. Now length of one coil is calculated by means of pi d. Okay, pi d means periphery of one coil. If you are going to consider that total spring, then one coil will have the periphery equal to pi multiplied by capital D multiplied by number of turns. That is how many number of turns are there. If you are able to calculate length of one turn, just multiplied by number of turns, it will give the total length of all coils. Got it? Let us consider that theta also. Sushant Jadhav. Sushant Jadhav, yes, what is your problem? Here written as a no, sir. Hi, whether it is related to the, do you have any question? Sushant, is it an answer for my question? Hello?
No, sir.
So, do you have any query or it is just answer for my question?
No query, sir.
Okay, no problem then. I thought you would have any query and that's why you are written as a no, sir. You have not understood it. Okay, let it be. So theta we are going to consider as a angle which has get deflected because of the torque T torque which has been applied while that spring is unwounded. Okay. So from this we can calculate that axial deflection of the spring, how much it will get deflect, and that will be the delta, that is axial deflection, is equal to theta multiplied by capital D divided by 2. Theta is nothing but the deflection which is taking place in that wire. Okay, म्हणजे आपण कॉइल अनवाउंड करताना जो थीटा डिफ्लेक्ट झाला असेल तो मल्टिप्लाइड बाय त्याची रेडियस, हे काय होईल की आपल्याला टोटल स्प्रिंग मधलं, ह्या स्प्रिंग मधलं डिफ्लेक्शन मिळेल. ती कितीने खाली आली किंवा कॉम्प्रेशन स्प्रिंग मध्ये कितीने कॉम्प्रेस झाली. ओके, त्यातल्या एका कॉइलचं अँग्युलर डिफ्लेक्शन, ओके, हे जर आपण कॅल्क्युलेट केलं थीटा एवढं, त्याला जर आपण ओके त्याला जर आपण डायमीटर किंवा रेडियस न गुणलं तर दॅट विल बी द टोटल डिफ्लेक्शन, म्हणजे ते कितीनं खाली आले, स्प्रिंग कितीनं कॉम्प्रेस झाली, हे कॅल्क्युलेट करता येईल. ओके, so we have calculated this deflection of that spring. Now again we are going to use the equation as T by J is equal to tau by capital D by 2. Now this J here the polar moment of inertia of that wire, where this J is calculated as pi by 32 small d raised to 4, pi by 32 d raised to 4, right? And this tau we are going to consider as a torsional rigidity, shear stress divided by deflection is equal to modulus of rigidity. Am I right? So we are going to calculate this tau is equal to g into theta divided by this total length of this wire. Okay. So this theta is calculated as T multiplied by L. This equation, this total equation we have written. Okay. So we are interested to calculate theta in terms of this T and J. So T divided by J into G into L. That will be the deflection which will be take place in the spring wire. Okay. Any doubt? Okay. So here this polar moment of inertia J is calculated as pi by 32 d raised to 4. G is the modulus of rigidity and this equation can be derived. Now, further if we substitute value of this L and J in the equation which we have derived. Okay. L how we calculated? Now this L is equal to pi d into N. Whereas T how we are calculated? It is not mentioned here. Okay. From the shear stress equation, we can write here value of T. Okay. W d by 2. That is nothing but the torque which is applied on that wire. That is force multiplied by radius into pi d. That is the L total periphery of one coil multiplied by number of coils. Okay. This will become T into L divided by J. J is pi by 32 d raised to 4 and G as it is, modulus of rigidity as it is. Okay. So this equation will become 16 because these 2 will be cancelled to this 32, that will remain 16. This 16 will go to the upper side. So it will be 16 W D, this D and this D will become D square into N. Okay. And this pi and this pi will get cancelled. So deflection will become 16 W capital D square into number of active turns divided by G, that is rigidity, modulus of rigidity, multiplied by wire diameter raised to 4. Okay. Now here from equation number 1, if we put value of theta, so this deflection can be calculated. So theta is equal to what, how we have calculated is delta is equal to theta into d by 2. Okay. So if you are not remembering this equation, the delta is equal to theta into d by 2. So we are putting value of theta. This theta will become delta divided by d by 2. So here we are going to put delta divided by d by 2. This divided by will go to the other side, will become multiply. So this 16W d square divided by G small d raised to 4 into N multiplied by capital D by 2. Okay. So this equation will become again 16 will be reduced to 8 W, this d square and this d will become d cube into N divided by G small d raised to 4. Okay. And if you are going to put this d, capital D divided by small d as a C, spring index, then it will become C cube and 1d will remain as it is, that is d. Okay, so this is calculated. Deflection is calculated. Further part we'll see to the next lecture. Very within 15 or 10 minutes we can finish this unit. Okay, that part has remaining, and I will take one problem based on this above design procedure, and we'll finish this unit. Okay, so it's 2:32. We'll stop here. Do you have any query? You can free to ask. If you have any query, you are free to ask. You can ask it. If not, I will take present it. Any question?